This video will look at how to make predictions using data sets. In particular, we're going to be looking at linear regression. So linear regression is a method for determining if there's a relationship between some sort of an explanatory variable. That's our input. The way I remember this is explanatory starts with x, and a response variable, that's my y. So if I do this correctly, for example, I've got years and the cost of bread in that year, I should be able to determine what that cost might look like in the year 2025, for example. Before I try to do any sort of things with larger data sets, I just want to make sure that I understand the basics of lines. So let's find the equation of the line that runs through the points 1, 10, and 3, 6. So sort of a reminder of what's going on for lines, I've got this equation y equals mx plus b. This is my slope-intercept equation. And the number next to my x represents my slope, or my rate of change. And this b value hanging out by itself, that's my y-intercept. Now my slope, this is the change in y over the change in x, or it's the rise amount over the run amount. And I'm going to use a symbol here that you might not have seen before, this delta. This little triangle symbol just means change. So I've got the change in my y values. I will subtract the y values and put that on the top. Over the change in the x, I'll subtract the x values and I'll put that on the bottom. So you may have learned the formula y2 minus y1 over x2 minus x1. That's exactly what I'm doing here. Now this is telling me how my y values deviate. And in stats, when I'm talking about how my y values or my x values deviate, that's talking about the spread, and that's something my standard deviation does. So this slope equation is directly related to the standard deviation that we've been studying in statistics. But let's just use this equation for what I have here. This is my second y value in the list, so I have 6, minus my first y value in the list is 10. My second x value is 3. My first x value is 1. I get 6 minus 10, or negative 4. I have 3 minus 1 is 2. 4 divided by 2, and I've got the negative there, so this will be a negative 2. I'm going to update the equation of my line here by plugging in this negative 2 for my slope, my m. So I have y equals negative 2x plus b. I'm one step closer to having this equation, but I still don't have this b. To find my y-intercept, I'm going to plug in a point, either one of these points. I'm going to choose 3, 6, and solve for b. Typically, I'm choosing the point that has smaller or easier to work with numbers. These both have relatively small numbers, so this 3, 6 is mostly because I think 3 and 6 is a little bit smaller than 10, but whatever works for you. For my y value, I'm plugging in 6. For my x value, I'm plugging in 3. And my b value, I don't know. I'm going to find it here. Negative 2 times 3 gives me negative 6. Adding this negative to the other side, so making it a positive on the other side, actually, gives me 6 plus 6 is b. So in other words, my b is 12. So plugging in this b into my equation here for my y-intercept, this tells me that my line is y equals negative 2x. It has a negative slope, it's decreasing. So it would go down 2 and over 1. And the y-intercept is 12. So if I graphed this, it would start at the y-intercept of 12, and it would go down 2 and over 1 from that value. Let's look at how I would view this data set here. I've got x values and y values. Now you can do this by hand, so you could, in theory, make a graph where you have the x-axis or the explanatory variable there as years, down, left, and right. And for the up and down values, you'd put your response variable, you'd put your cost of bread. I'm going to use technology instead here just because I think it'll make a slightly nicer graph. And I'm going to be doing this in Geogebra. Geogebra is a free program that you can download on any operating system. I've already got it downloaded here. So I'm going to open this thing up. And I'm going to choose the option for spreadsheet. Inside of spreadsheet, I've got this spot here where I can type in my values. I'm going to put my x values in the spot where it says A. And my y values, I'm going to put that into the spot that says B. Now, cheating a little bit, I've already typed this in, so I'm just going to actually copy and paste it. There we go. And I've got all of my x values and all of my y values. Next step. Select the data. My process of selecting data will be to click and highlight it. After I do that, I'm going to click the box up at the top that kind of looks like a histogram. And I'm going to choose the option for 2-variable regression. So I'm going to have some sort of a cloud, and I'm kind of trying to find the equation that goes through that cloud as best as possible. When I do this, I get a scatter plot that looks something like the following. So just kind of looking at this scatter plot here, it appears that the cost stays kind of stationary for a while. It's going up, but kind of slowly. And then it grows faster and faster. And then boom, in 2010, it's at the highest that it is for the data set at $2.79. And then it bounces back down for a while. So describe the scatter plot in detail. Okay. I'm going to describe 3 things about it. I'm going to describe the shape of the graph. I'm going to describe the direction of the graph. And I'm going to discuss the fit. So shape. This is the underlying thing that you can see when you kind of squint your eyes and look at it. Now, the nice thing about Geogebra is down at the bottom, you can actually choose a whole bunch of different equations. So for example, you might think that this thing looks like a line. I guess it kind of looks like a line if you squint your eyes. I'm noticing that it's missing some of these values, though. So instead of line, let's choose exponential. Looks like it's much better for exponential at the start, but it's not perfect at the end. Maybe I think it looks like a log. Oh, log looks awful. Maybe I think it looks like a power function. Power function looks okay. Maybe I think it looks like a sine curve. That doesn't look that great there. So out of all these options I've been kind of toying around with, and I would encourage you when you're doing this to just kind of tinker and see what you get for your best fit. I think exponential looks pretty dang good. So for shape, exponential. And direction looks like this is an increasing graph. So increasing, and another way to say that is there's a positive association. Think of that kind of like slope. If there's a positive slope or a positive association, it means your data plot is going up. If it's negatively associated, that means your data plot is going down. Now, this doesn't mean that it's always going up. Some of these points go down, but the trend line itself is increasing. And fit, I think this is a pretty decent fit. It looks a lot like this exponential at the beginning, and these endpoints don't miss it by a lot. So I might say that this is a good fit. If you did not see this thing as an exponential, but you saw it as a line instead, that's okay too. This is kind of like looking at a cloud. You might see something different as the person next to you, and that's all right as long as you're describing everything based off of what you see. So let's say we think maybe it's linear. In this case, it's still increasing, or there's a positive association. As far as the fit is concerned, not awesome. I see some spots that it goes through perfectly cool, but otherwise I've got several things that are kind of too low or too high. So I would say this is an okay, maybe poor fit. I'm hoping there becomes a numeric way of kind of measuring if something is a good fit or not a good fit. But let's just do one more example where we talk about shape, direction, and fit. So going to my overhead here, when we're describing a scatter plot, we talk about shape, what do you see when you look at the thing? Direction, is it mostly increasing or decreasing? Fit, how much does it look like that? So we'll do one more. So here is my scatter plot. Whatever this x value represents, this is my explanatory variable. Whatever my y value represents, this is my response variable. If I'm describing what I see here, to me, it looks like a cloud of points. I don't think there's anything that's going to be too amazing, but if you kind of squint your eyes and look at the middle of it all, I would say this thing kind of looks like a line. So for shape, this looks linear to me. Direction, looks like this thing is going down or it is decreasing. Equivalent to say that it is negatively associated. And for fit, ooh, in some ways this is better than my last graph because at least this looks a little bit more like a line to me. But at the same time, there's so many points that are around it that I don't really know for sure how I feel about this. I might say this is an okay fit, but I certainly think that you could have a better fit. And this okay, poor, good, I really hope that there is some way to mathematically pin this down because this still feels a little bit too wishy-washy to me. And luckily there is. So when describing the fit of a linear relationship, instead of using language like okay, poor, or good, we can measure this using a terminology called correlation. And this tool, correlation, which is represented by the letter R, tells us if something is a strong or weak relationship. Here are some properties about R. R is a number between -1 and +1. So R is some number on the scale -1 to +1. If your R is bigger than 0, think about having sort of a positive slope. this would tell you that your line is increasing. If your R is less than 0, this tells you that your plot is decreasing. If your R is close to +1, that's positive, so it's increasing. And close to 1 means it's almost perfectly linear. Likewise, if your R is close to -1, it's also almost perfectly linear, but that's decreasing. So this is kind of a spectrum where both -1 and +1 are considered good. 0 represents there being no correlation between the values. That's either a cloud of points or some sort of horizontal line when there's no clear relationship between those variables. So -1 is good, +1 is also good, 0 is bad. So this is kind of like a reverse Oreo. The inside is bad and the outsides are good. I'm going to give you several different values for R here. And then we're going to go ahead and see if we can match these values of R up to some sketches. And if you're following along at home, after I do these doodles, I'll give you a cue to pause your video. I would encourage you to do so and see if you can match these things up for yourself. So for this first graph, suppose it looks like this. Second graph, suppose it looks like this. Third graph, let's say it looks like this. And fourth graph, let's say it looks like that. All right, if you're following from home, go ahead and pause the video and see if you can match all of these different R's up to the graphs below. Okay, I'm going to go through this and let's see how we did. First thing I noticed, this is the only one that's decreasing, and this is almost perfectly linear except for these 2 or 3 spots here. So I would say this has an R that's negative because it's going down. This immediately limits me down to just this one option of -0.95, but that seems like a really good value for that because this is so close to being perfectly linear and decreasing. Looking at these, I have 2 R values that are telling me I have some sort of a linear relationship that's increasing. 0.8 means this looks more like a line. So of these 2 options, I think C looks like it is more linear. It might be the case that B is steeper, but we're not measuring steepness here. We're measuring how close it looks to a line. And the closer it looks to the line, the closer your R is going to be to either -1 or +1. In the case of this, where you just have straight up trash, you will have an R close to 0. There are ways of calculating R by hand. Here's the formula for calculating R by hand. But you can also use technology to do so. Let me show you how to get R using Geogebra. And then I'm also going to show you how to do this using your graphing calculators. So inside of Geogebra, I've done my linear regression. So after you have done your scatter plot, and after you select the option for linear, you're going to go up to the top and you're going to hit the button that looks like sigma x. That's right here. I'm going to click it. It gives me this menu over to the side, and the value I'm looking for is this R. So for the example involving the bread data, I have an R of 0.8657. This is positive because our data is increasing. It is not perfectly 1 because this is not a perfect linear fit. Okay, let me show you how to do this now using your TI-83s, your 84s, or 89s, any of those sorts of calculator. And let's start with the TI-83 and the 84. 83 and 84, folk, I just want to show you one thing that you have to do before trying to do anything else, and that's you have to make sure that your diagnostic is on. So hit the catalog button is here in blue, hit second and then 0. So TI-83, 84, I'm going second, 0. And then I'm going to scroll down until I get to where it says diagnostic on. If you type the letter D, it jumps straight to D for you. And you're looking for diagnostic on. If you do not have diagnostic on, when you go through this process to do linear regression, it's going to calculate your slope and your y-intercept for you, but it would not calculate your r and your r squared. So if you ever run into an issue where your r and your r squared is not showing up, go through this process again just to make sure that it says done for diagnostic on. Okay, you only have to do that once. After you do that, type in your data by going stat and then edit. And I'm going to type that into my calculator here, stat, and then edit. And list 1, you're going to type in all of your x values. And in list 2, you're going to type in all of your y values. If you have numbers already in your list, you can select the top of the list and hit clear and enter. One thing you don't want to do is you don't want to hit delete. Here's why. Do you see how I have list 1, list 2, list 3, list 4, and list 5 here? I'm going to hit delete where it says list 3. And now it goes 1, 2, 4, 5, 6. If that drives you a little bit crazy, you would have to manually go through and delete and rename all of your lists just to get them in the right order there. So don't hit delete. Your calculator will be very literal with you, and it will think that you no longer want a list called whatever your list is called. I'm going to pause the video and type in my data here. I'm going to ask that you do the same. I have typed in my data. Now, one really common mistake with linear regression and trying to find your R and your R squared, whatever R squared means, we'll figure that out in a second, is something called a dim mismatch. That happens when you have too many x values and not enough y values. So for this next step, to come up with my R, I'm going to go stat, calc, and I'm going to choose the option for linear regression ax plus b. I'm going to do this correctly once, and I'm going to do it incorrectly another time, just to show you what can go wrong. So stat, calculate, and I'm choosing this option that looks like ax plus b, because that's kind of like mx plus b. That's sort of my equation for a line. If you're on an 83, it might not ask you for any of this, and that's okay. Just hit enter, and it'll give you what you want. It will assume your x values are in list 1 and your y values are in list 2. If you're on an 84, make sure it says L1 and L2 here. Your L's are in blue, so need be, you could hit second 1 to have list 1 show up, and second 2 to have list 2 show up. I'm leaving everything else blank though. I'm going to calculate. And I would recommend that you write down everything that you got here on the screen. This is giving me an A, a B, an R squared. Don't know what that means, but at least I have it, and an R. The R, I will double check. I got an R of 0.866. I have an R of 0.866. I'm feeling pretty good about that. Let's do this now with it slightly incorrect. So going into my data set here, for this value, I'm just going to type in an extra number. And I wanted you to see what happens if you have too many x values or too many y values. Now, when I try to do my linear regression, ax plus b, and I try to calculate it, it says error, dimension mismatch. So this error occurs when you do not have the same number of x values that you do y values. So make sure your lists line up there on the bottom, or you will run into some issues. Okay, TI-89. Let's take a look at how to do this using your calculator. You are going to go into StatList Editor. So I'm hitting Apps, and then I'm choosing the option for StatList Editor. This immediately gives me my list 1 and my list 2. Inside of where it says list 1, clear and enter if you have steps typed into that. You're going to type in all of your x values. In list 2, you're going to type in all of your y values. Using the data that I had here, for example, 2, I'm going to type this into my calculator. I'm going to pause the video while I type this into my TI-89. Okay, I've typed my x values in list 1, my y values in list 2. I'm now going to calculate. That's F4 for calculate. I'm choosing the option for regression. And then I want to match things up with my other calculators as much as possible. So I'm going to choose the option for linear regression ax plus b. That's like mx plus b. It'll ask me where my x list is. Hopefully this says list 1. If not, spell it out, list 1. Y list is list 2. Again, make sure to spell that out. I'm leaving everything else blank and I'm just hitting enter. This should give me my A, my B, an R squared, and an R. I seem to be getting the same results for everything. I got a slightly different value for my R earlier when I used Geogebra. So going back through Geogebra, I noticed that this should have been a 0.12 instead of 0.15. I fixed that. I'm now getting the same R for all of these things. Fantastic. And that R is 0.8664. So this is not quite 1, so it's not perfect, but it still might be an okay fit. Unfortunately, I have 2 things that are considered good, both -1 and +1. So R might tell me if the line is going up or down, but it doesn't for sure fix the issue of determining if something is a good fit or not a good fit, at least not on its own. If I were to square R, however, then both the -1 and the +1, -1 squared will give me 1, and +1 squared will give me 1. So now all of my good values when I square it will point to the same number. 0 squared, well, 0 was bad, and when I square it, 0 continues to be bad. So 0 is the worst fit you could possibly have for an R squared, and 1 is a perfect fit. Throughout these videos, we've seen a lot of numbers from 0 to 1. These things are actually percentages. So 0 represents something that kind of looks 0% like a line. 1, this means that my data set looks 100% like my line. The technical way of saying this is R squared is the percentage of variation accounted for by my model. And I want to know where things are coming from. So the larger the R squared, the better. Because anything that you don't know, that's just due to luck or a lurking variable or something else that you can't describe. So for example, we had an R of 0.8664. We're going to square this R. And let's see what we get. And I find when you get this, it helps to think of this thing sort of like a letter grade. I'm getting 0.75 or so. So it's sort of like 75%, kind of like a line. 75% of the variation is accounted for by this model, which means 25% of the variation happens, and I don't know why it happens. This is my personal opinion, but I feel like if I got something that was an 85% or better, I would consider that to be pretty good. I think something between 75 and 85% is okay. I think anything 75% or less is poor. So for R squared for this cost of bread example, I would describe this as being borderline okay, poor fit. But I now have a numeric way of kind of checking things out. Now, just a note, your calculator, when you did that linear regression thing, let me pull up my 84, it gave me both an R and an R squared. So your calculator will actually automatically give you all of these values. So on mine, just writing down everything that it told me, it said y is equal to ax plus b, a is equal to 0.0281, b is equal to negative 54.6780 or so. My R squared, this is the percentage of variation, was 75.06, not a great fit. And my R is 0.8664. So this R is roughly telling me if my data is going up or down. This is positive, so this is going up. This R squared is telling me the percent fit. So 75% of the variation is known. And looking at this, the number next to the x is a slope, so this a value it gave me is the slope of my line. And this b value hanging out on its own is the y-intercept. So this means I actually have a line already that will allow me to make predictions about what should happen for the cost of bread. And that line is y equals ax plus b. So y equals my a is 0.0281x plus a negative, so minus 54.6780 or so. When I'm using this line, x is equal to the year, and y is equal to the cost of bread. Let's use this line to make some predictions. So how much did bread cost in 1960? So 1960, that's the year, that's the x. So I'm just going to plug that into this equation. And let's see what we get. Now, I don't expect these predictions to be perfect for a couple of reasons. First off, my R squared isn't that great. And it's pretty rare that any prediction is perfect. When I did this, I got 0.398, which would be about 40 cents or so. Let's see what's going on for the year 2016. Same idea. I'm going to plug 2016 in for the year. In 1960, I thought bread should cost about 40 cents. In 2016, I think bread should cost about $1.97 or so. And let's see how much bread should cost in the year 1800. I'm putting 1800 in for the X value for the year. I'm typing that into my equation. And when I do so, I get negative, ooh, what? Okay, negative 4.098. And this is dollars. Now this last one's a little bit odd for me because negative would mean I go to buy bread, I ask them, hey, how much is this? And they give me $4 and roughly 10 cents to take the bread away. That seems like a pretty good deal. Now, some of these predictions are obviously going to be better than others. I don't think it was negative $4 in 1800. 1960, well, this one I can actually check because 1960 was one of the years of my data set. It was 22 cents. I'm off by a fair amount there, but it's still more reasonable than at least this negative. So there are two different types of predictions. And these types of predictions will impact whether something is good or not good. One type of prediction is extrapolation. This is usually the more desirable of the two types of predictions because it predicts something that will happen in the future. So this is predicting outside the data set. So if there was extra credit, that's something that's outside of the normal credit that you get for a class. Extra means outside. So looking at my years, 1960 falls between 1930, the lowest and the highest. 2016 is not part of this data set, so this is outside. 1800 for sure is not inside of my data set. So these last two things down here are extrapolation. While these are more interesting, a bit of a what if to be like, well, what do you think it was like in 1800? And 2016, it feels like I should be able to make a reasonable prediction about that year given the data set I'm working with. This tends to have a bit more air to it. In fact, your stronger predictions are going to be the ones that happen inside of your data set, and that's interpolation. So this is predicting inside the data set. But even this type of prediction will not be perfect. We're going to see that error is an unavoidable part of making these predictions. So this is how I do this using technology. A couple of things that I still want to look at besides just cranking this thing out in Geogebra or my calculator here is how do I reasonably do some of this by hand or at least have an intuitive understanding about where these numbers are coming from so it doesn't feel like magic. And how can I analyze what could go wrong with these prediction types? So something to keep in mind. In stats, the equation of a line, or in general, the equation of a line is y equals mx plus b. And here's what we're doing. In stats, my lines look like y hat equals b1x plus b0. And if you're wondering, well, why isn't it just the letter y here? Well, when I'm looking at this picture, all of my data points, these are actual things that have happened. So my data represents the true values for y. Your line itself is predicting what should be happening, so your line is actually a y hat. In general, a hat is indicating that's an estimate for something or a guess. So on this previous page where I had y equals ax plus b, this is really a guess. That should have a hat. Y equals, there is my equation. This isn't a guess for an equation. It has a hat. I am predicting, and I'm seeing that some of these predictions are off. So I'm going to label them as y hat just to kind of say, hey, I could be a little bit off with any of these values. B1, that's the symbol next to the x, and that represents my slope. Now, I'm using B1 instead of the letter M for slope here because I could have more than one factor that goes into something changing. So the year affects the cost of bread, but so does the cost of flour, the cost of water, the cost of gas, how far I'm shipping something, how much it costs to package it. And each of these things could have their own individual slopes. So if I was using different letters like an M, N, O, I would quickly run out of the alphabet there. So B1 is just saying, this is my first slope that I care about. B0, this number hanging out on its own, this is my y-intercept. How do we find slope? Well, slope, which previously we'd been calling M, we had as rise over run. Now in stats, it's still going to be the same thing, but we're using the letter B1 for it. And it's going to be the change in my y values over the change in my x values. My rise over my run. So this is asking, how do my y values deviate and how do my x values deviate? And I answer that by looking at the standard deviation for that y value list. I do value minus center squared, I add those things up, I divide it by n minus 1. That should give me my variance. Taking the square root, I have my standard deviation. Standard deviation for x values, that's how my x values change. Bit of a problem though. Note, my standard deviation for my y value and my standard deviation for my x value, these are always positive numbers. But I can have a slope or a line going up or down. So I need a way to sort of have a toggle switch, something that tells me if my line is going to be increasing or decreasing. And just reviewing some of the earlier things my calculator gave me, r squared is the percentage of fit, but r is this value that tells me if my line is increasing or decreasing. So my equation for slope is going to be r. This is a toggle switch. It just tells me increasing or decreasing. Standard deviation of y. This is the change in my y values over standard deviation of x. This is the change in my x values. So I'm going to write down this equation, and we're going to use this in a second. But slope is r standard deviation of y over standard deviation of x. Rise over run times r to tell us if it's going up or if it's going down. How do we find the y-intercept? Well, previously, we find the y-intercept by plugging in a point. So when I'm looking at a cloud of values and I'm trying to come up with my line, I need some point that I can plug into the equation to figure out where it's crossing. This point that I have on my line for every single line is going to be in the middle of your x values and in the middle of your y values. Your predictions are strongest near the center. The further out you get from your data set, the worse your predictions are going to be. So X bar, Y bar is always on your line. It's in the middle of everything. So my equation for my line looks like y hat equals b1 x plus b0. And I'm trying to solve for my y-intercept. And I'm going to plug in my y of this point and my x for this point. And I'm going to get the y-intercept by itself by undoing the addition. I undo the addition by subtracting this amount over. So if I take the average for my y's and I subtract the slope times the average for the x's, this will give me my y-intercept. So this equation I can use for finding the y-intercept, but I would encourage you to just plug in your average for both x and y and solve instead of memorizing this equation. Let me show you what I mean by this. So I'm going to calculate the slope by doing r times rise over run. And I'm going to find my y-intercept by plugging in the average for x and the average for y. So I want the equation y equals mx plus b. That's what I'm thinking in the back of my head. But in stats, the notation is y hat is equal to b1x plus b0. I'm going to start by finding my slope. My slope, b1, is I'm going to take my r. I'm going to multiply this by the change in x on the bottom, then the change of y on the top. R for this problem is 0.8, so this tells me that my line is increasing. My rise, or my change in my y values, is 3. And my change in my x values here is 5. Typing this into a calculator, I have 0.8 times 3 over 5. This gives me 0.48 for my slope. So my equation now looks like 0.48x plus whatever my y-intercept is. I've solved for the slope so far. To find the y-intercept, we're going to plug in our point, average of x, 10, and average for y, 4. So I'm going to put the 4 in for the y, and I'm going to put the 10 in for the x, and I'm going to solve for the y-intercept. Multiplying by 10 moves the decimal over, so this is the same thing as 0.48. Make sure I get my decimal correct there. Times 10 becomes 4.8. I want to undo addition, so I'm going to subtract this amount over. And 4 minus 4.8 gives me negative 0.8 or so. Adding this y-intercept to my equation, my line looks like y hat equals 0.48x minus 0.8. Okay, this says let's verify our cost of bread equation. Fine, let's do that. So earlier I found my R using technology to be 0.8664. Let's see if we can find the average for x, the standard deviation for x, the average for y, and the standard deviation for y. And I can use technology to do that, or I can do it by hand. I'm going to cheat a little bit, and I'm going to use technology. If I'm on something like a TI-84 and I want to calculate the average and standard deviation for this first list, I'm going to go Stat, and then I'm going to Calculate, and I'm going to choose the option for 1-var stats. I want to find everything for this first list, so I'm leaving it as list 1. I'm going to go down to Calculate, and this gives me the average year. And this seems reasonable. The middle of the years is probably about 1974.5. The standard deviation for the years is approximately 29.4816. If I did the same thing again here, Stat, Calculate, 1-var stats, but I hit second 2 to pull up L2, this will give me all of the information for the y values. So the average y is 0.839, and the standard deviation for my y is 0.9567 or so. Let me show you how to get the same thing using a TI-89 and also in Geogebra. In my TI-89, let me zoom in. I've got all of my x values typed in list 1 and all of my y values typed in list 2. I'm going to choose the option for Calculate, so F4 for Calculate, and then 1-var stats. If it says list 1, LIST1, and then enter, this is giving me the average for the x's and the standard deviation for the x's. And this is exactly the same thing I got on my TI-84. If I do the same thing again and I go up to Calculate, F4, 1-var stats, and I change this to the second list, this will find my average for my y values and the standard deviation for my y values. Again, that seems to be matching up. If I wanted to do this in Geogebra, I've got my values over here. I could select the numbers that I care about. I can go up to the top and I can look at just one list at a time. And I'm going to hit the sigma x thing. This is how I find all of my numbers in Geogebra. And it will give me my average, 1974.5, and my standard deviation of 29.4816. I can do the same thing for the second list. I can highlight the second list. One variable I'm analyzing here. I'm hitting the thing with that sigma x, and it gives me both my average, 0.839, and my standard deviation, 0.9576. So that's the way that I can calculate those values inside of Geogebra. I'm pulling back my lineup for something later. Now that I have all of these individual values, let's use these equations that I have to calculate my line by hand. I'm going to start with sort of the template. Y hat is equal to my slope times my x plus my y-intercept. And I'm going to start that process with finding the slope b1. I'm going to take my r, and I'm going to multiply that by the standard deviation of y divided by the standard deviation of x. So I have my r times the change in my y over the change in my x. I'm going to type that into a calculator and I will see what I get. And when I typed this in, I got 0.0281 or so. So my equation looks like y hat equals 0.0281 x plus whatever my y-intercept is. To find my y-intercept, I'm going to plug in my averages. I'm going to plug in the average of the x in for the x. That was the average year. And the average of the y in for my y. This is the average cost for bread across all time. So I've got 0.839 is equal to 0.0281 times my x plus b0. If I want to get rid of this addition, I can just take whatever this number is and subtract that from the other side. So I'm going to have 0.839 minus whatever this number ends up being. And that's going to give me my y-intercept. So let's type that into a calculator and see what we get. And when I do this, I get negative 54 point approximately 64 or so. Now, up to a little bit of round off error, I'm getting y hat is 0.0281x. This is plus a negative, so minus 54.64-ish. And when I did this with technology, with nothing but a calculator to come up with a line all at once, I got something really, really comparable. The only difference is up to a little bit of round off error. Now, if I happen to already know all of this information, this ends up being the fastest way of doing the problem. However, if I have a long set of data, using a calculator is by far going to be the cleaner and faster way of doing that. But I wanted to show you both ways, so that way you can kind of do the problem regardless of what you're given. Predict the cost of bread in 1970. Okay, let's do another prediction. This 1970, this is a year that is inside of my data set. So this is going to be an example of interpolation. And interpolation is usually the good type of prediction because it's inside. But let's type it in and see how close we are. When I did this, I got approximately 0.717, so about 72 cents or so. Let's look back at the first page with all of this data and see what we actually have in the year 1970. So I thought bread should be about 71 cents or so, but I'm seeing that the actual cost of bread is closer to 25 cents. So it looks like I have a considerable amount of error. I call that error my residual. And residual E for error, I'm going to take whatever the actual value is from the data, and I'm going to subtract whatever I got for my prediction. So for example, if I want to know what the error in the prediction was for 1970, my residual, or my error amount, I'm going to take what it actually was in that year. In 1970, it was 25 cents. And I'm going to subtract the amount that I predicted to see how far off I was. So in this case, 25 cents, take away 71.7 cents. It looks like I have an error amount of about 47 cents or so, which all things considered, this seems like a lot of air. Some values are going to have higher residuals than others. And one neat thing about Geogebra is it can actually do a graph of your data like this, but it can also do something called a residual plot. And by doing this, you can actually see the areas where your predictions are going to be the strongest, where you have very little air, and where your predictions are going to be the worst, where you have a lot of air. Notice for 1970, I have approximately negative 0.467. That's matching up with the value that I got by hand, but that is by no means the worst amount of air. It seems like in the year 2010, if I were to try to make a prediction using my line, let's look back at the line, I'm going to be off by a massive amount for that value. In general, this linear fit is not going to be very good for this particular data set. I could do these residuals for any type of model. So if I thought that this thing was really exponential, I think you would find that your residual plot is considerably better. I have less air. That's the goal of regression in general, is to try to minimize the total amount of air as much as possible. I hope this has given you some tools for coming up with these lines of best fit, and I hope this has given you some intro to some of the language related to linear regression models.